In Deuteron, we have already discussed the Deuteron theory based on Schrodinger equation, and we got an equation. And based on this, we will be trying to define the Deuteron radius. Also, we have the properties of spin, parity, magnetic dipole moment, electric quadrupole moment, etc. And we have a look on these topics also. So, first is Deuteron radius. And we use the external exponential function, that is the nuclear radial wave function with the small letter r greater than capital R. That means greater than the nuclear force range, which is about 2.1 femtometer. And we have mentioned it as the region second. And it was given by the following equation. And we want to find out the radius of the deuteron that we are marking as R subscript D. So this was the equation we got for the second region, or small r greater than capital R. U r equal to C e raised to minus K2R plus D e raised to K2R. These terms K2 are defining based on your mass, Weyling energy, and potential, etc. That is known to us. And we have mentioned that we have to take this D as 0, and this is our equation. UR is C e raised to minus K2R. So this was only applicable for the first region. And if we extend backward the exponential function up to R is equal to 0, then the distance at which U of R falls to 1 by E times its value at R is equal to 0 is taken as the measure of Deuteron radius. This is a way of defining the Deuteron radius, because Deuteron is that means the two nucleons can be at any distance, and we have already seen that it is a weakly bound system. That means our 2.1 femtometer or 2.1 Fermi is the nuclear range actually, but your nucleon separation, or the radius of the deuteron, or the separation between the proton and neutron, can be greater than this value or less than this value. That means it can be outside the potential well and it can be inside the potential. So your definition, sometimes it is also known as the root mean square radius of deuteron, etc. So that D you are defining as, it is a value of UR at R is equal to 0, when it is a distance at which it is falls, or it is decreasing to 1 by E times its value at R is equal to 0. This is the usual way of defining so many quantities. And for this, we will be using the value of UR, that means the radial wave function at the region 2, and we are actually moving it backward, or we are extending it backward. So this is the way we are defining UR at R is equal to RD is what? 1 by E times U of R at R is equal to 0. That means this was our definition. That is, this is the equation C e raised to minus K to R, and here you can substitute RD in place of R. So C e raised to minus K to RD is equal to 1 by E times C e raised to minus K to R, where R is equal to 0. And when this R is 0, it is minus K2 into 0, and E raised to 0 is 1. So it is 1 by EC. So you can cancel these two E's. So E raised to minus K2 RD is 1 by E, or E raised to minus 1. And taking logarithm, you can get it as minus K2 RD is equal to minus 1. or K2RD is equal to 1, or RD you can consider as the reciprocal of K2, 1 by K2. And what is K2? K2 is already defined as root of 2mb by h cross square. So RD will be root of h cross square by 2mb or h cross by root of 2mb. In this, m is the reduced mass of deuteron. It is normally half the proton mass. And this B is the binding energy, which is already known to us as 2.225 MeV. H cross is known. So by substituting these values, you can find the value of RD as 4.31 femtometer or 4.31 Fermi. So this value is about twice that of the range R. This explains that deuteron is a loosely bound system. That means average distance will be always greater than the nuclear range. The probability of finding the neutron and proton within the internucleon force range is small. That means internucleon range means it is 2.1 femtometer, and that is only about 30%. The neutron and proton stay outside the range of NP force nearly 70% of the time. This shows that the deuteron is rather loosely bounded structure. So we have defined that term and we have shown that our deuteron is a weakly bound system. And the spin and parity we have already described, and initially we have mentioned that the spin of nuclear you are taking as, say, that I equal to, you are taking as a sum of Sn plus Sp plus L, where this Sn is the spin of neutron, Sp is the spin of proton, and L is the angular momentum of nucleons. That means they are a system, proton-neutron system. It's angular momentum. And we have derived our simple theory of neutron by assuming this L as 0. So the total angular momentum I is not Z, I of the deuteron should have 3 components. Sorry, this is capital I. The individual spins Sn and Sp of the neutron and proton, which is equal to half, and the angular momentum L of the nucleons as they move about the center of mass I, you can write as Sn plus Sp plus L. When we solved the Schrodinger equation for deuteron, we assumed L is equal to 0. So the measured spin of deuterons is 1. This we have already done. Since the neutron and proton spins can be either parallel, that means for a total of 1, or anti-parallel, that means 0, there are 4 ways to couple Sn, Sp and L to get a total spin of 1. That means Sn and Sp parallel, that means half plus half as 1 with L equal to 0. So we will be getting as Sn plus Sp plus L as 1. That is I is equal to 1. Sn and Sp anti-parallel. That means Sn, if one is plus half, other is minus half. So Sn and Sp will give you 0 plus L with L is equal to 1. And then Sn and Sp parallel with L is equal to 1. This case we will discuss later. That means 1 plus 1 equals 1. That is already a case known to us. Or Sn and Sp parallel with L is equal to 2. That means Sn and Sp means half plus half is 1. And L plus 2, L is equal to 2 must be in the opposite direction. So 1 is 2. In the opposite direction you have 1. So it is 2 minus 1, that is 1. So these are the cases. Sn and Sp parallel. Sn, Sp parallel. L is 0. So half plus half as 1 plus 0 is 1. Then Sn and Sp anti-parallel, half. This you can take as minus half and 1. So half minus half plus 1 is 1. And our third case, Sn and Sp parallel with L is equal to 1. Sn half, Sp half. and L equal to 1. So half plus half is 1, and this is also 1. So Sn plus Sp plus L equal to this value of this vector, and if it is an equilateral triangle like this, you can get this value as 1. So Sn plus Sp parallel with L is equal to 1 is also possible. And Sn and Sp parallel, half plus half you can take as 1 with L is equal to 2. That means you are considering L in this direction. So if it is the plus value, L is equal to 2, this must be half. So minus half plus 2, that will be 1. So you got 3 conditions. 4 conditions. Then we have only the condition that your I is 1. And for that I is equal to 1, L can be either 0, 1 or 2. We got these conditions that as A, B, C and D. And in A, value of L was 0, and in B and C, value of L was 1, and then the last case, L is equal to 2. And another property of Deuteron that we can determine is its parity. Parity can be either even or odd. So even parity means there is no change for the nuclear wave function. Odd parity means nuclear wave function is getting as the -1 in parity change or parity reflection. And the behavior of the wave function when you are changing it as R to minus R, this is the condition. By studying the reactions involving neutrons and the property of photon emitted during the formation of deuterons, we know that its parity is even. So parity of neutron is even. This is already mentioned. So the parity associated with orbital motion you can take as -1 raised to L. Therefore, even parity for L is equal to 0. That condition you are calling as the S state, and L is equal to 2, which you can call as the D state. That means -1 raised to 0 equal to +1, as well as -1 raised to 2 equal to +1. And odd parity for L is equal to 1. That means the P state. That means -1 raised to 1 is -1. That means your parity is odd, which means that it is the -1 value. So the observed even parity allows us to eliminate the combinations of spin that include L is equal to 1, leaving L is equal to 0 and L is equal to 2 as possibilities. The spin and parity of the deuteron are therefore consistent with L is equal to 0 as we assumed. But we cannot exclude the possibility of L equal to 2. In simple theory, we haven't considered the L is equal to 2 condition. Next is magnetic dipole moment. The total magnetic moment is the combination of neutron and proton magnetic moments. Both orbital and spin angular momentum contribute to magnetic field. If L is equal to 0 assumption is correct, there should be no orbital contribution to the magnetic moment of deuteron. That means you can have equation like this. And how you are getting this equation is familiar to you like this. You are normally calculating mu as this equation. You are normally writing as magnetic dipole moment equal to current into area. Actually, number of turns is also there. Just I into A. And if R is you are taking small letter r as the radius, pi r square can be the area. And the current, the charge, here charge is E because you have proton and neutron, which charge is just E, and E by charge by time. And for finding time, if it is moving with the velocity v, you can see that in a time That means it is moving with the velocity to complete a circle. And that time required you can consider as the time period. So your v will be equal to 2 pi r by time, and time will be equal to 2 pi r by v, that you are substituting here. So your equation will be EVR by 2, and you can multiply this with the mass. So MVR into E by 2 m, and that mv into r you can consider as the angular momentum. That means E by 2m into this L here stands for the angular momentum, and that angular momentum can be either spin angular momentum or orbital angular momentum. And multiplying this with h cross, you can write it as EH cross by 2m into L. And this EH cross by 2m, if you are here substituting the value as mass of proton, EH cross by 2m P, which can be called as the nuclear magneton. And as you know, if it is the mass of electron, you are calling it as the Bohr magneton. So this is the equation. E is equal to normally mu n into L. That you can write. Mu n is the magnetic magneton, nuclear magneton. But you have already the concept that all these are not point charges. So in order to remove that difficulty, you are normally multiplying with the factor known as the G factor. So that you are writing as G into L. GL is the angular momentum factor into L into mu n. So this is the equation. And if it is for spin, you can write it as GS. In place of this L, you are simply writing as S is the spin angular momentum and L is the orbital angular momentum into mu n. So these are the equations to find out the magnetic moment due to orbital motion and spin motion. So this is the condition. And here you can see it as GLL mu n. So for proton and neutron, we are eliminating the L condition because we know that L is equal to 0. So our usual expression will be GS. In this, we have to use this equation GSS mu n. And if you are writing that S as S in terms of H cross, that means this will be half H cross value. You have to divide it with H cross also. So there is multiplication of this H cross in numerator and denominator. And for neutron, you are writing it as GSN mu. This is the nuclear magneton, and the small n stands for neutron. So GSN mu n by H cross into Sn. And for proton, it is GSP mu n by H cross into Sp. And these values are experimentally determined values. GSN, it is a minus value, and the GSP equal to 5.58. This is the Bohr nuclear magneton for proton. I think you are familiar with this number 5.58 in your spectroscopy classes. This we have already mentioned. So we take the observed magnetic moment of the or set component of mu as the spins, which you can take as half H cross. So if these are half H cross, that H cross and H cross cancels. So you will be getting the equation as half mu n into GSN plus GSP. You can substitute the value of GSN and the GSP here. And you can multiply it with the mu n, and by divided by 2, you can get the value nearly as 0.879804 mu n. We are actually not multiplying with the mu n, just writing in terms of mu n. In terms of this, quantities are known. And the observed value that you can measure is simply 0.85. There is a difference there. This is 0.8574 and this is 0.879 mu n. But it is in that you can say that it is in quiet agreement But exact agreement with the calculated value is not there. So it is in good but not quite exact agreement with the calculated value. And what may be the reason? We can assume that the discrepancy to arise from a small mixture of d state, that is L is equal to 2 in the Deuteron wave function. Here we have not considered the orbital angular momentum part. And if you include that also, we can correct this, and that is our assumption. And the wave function of Deuteron you are not writing as psi, and that psi is a combination of L is equal to 0 and L is equal to 2. And there is a probability for occurring this L is equal to 0 state and L is equal to 2 state. That probability you are writing as AS is the probability for L is equal to 0 state. That means the S state. And AD is the probability for L is equal to 2 or the D state. That means your psi will be a combination of, or you can write it as AS psi L is equal to 0 plus AD psi L is equal to 2. And if this has the probability of half, you have to write it as half and half. And if this is 90, it will be 0.9. This has 10% probability, it will be 0.1. That's all. So this AS and AD are the probabilities of S and D states respectively. So calculating the magnetic moment from this wave function gives. So your mu will be AS square. That means for finding any quantity, you have to square the wave function. That is why you are getting it as AS square of mu into mu of L is equal to 0 state plus AD square mu of L is equal to 2 state. And this value we already got as this value 0.87984 mu n, and it is higher than the expected one, plus AD square mu into L is equal to 2. So this value can also be calculated using some experiments. So you have this value and this value. So a combination of these two will give the correct value of mu. That means 0.8574. It is not L is equal to 0, not calculated the value. It is 0.879804, not this value. It is a mistake. You have to correct this. So this value also calculated. Then the observed value is consistent with the AS square is equal to 0.96 and AD square is equal to 0.94. If you substitute this value as 0.96 and this as 0.4, and if you substitute the values of L is equal to 0 mu value and L is equal to 2 value, you will be getting this correct value 0.857. That means AS square is equal to 0.96, AD square is equal to 0.04 means 96% time it is L is equal to 0 and only 4% time it is L is equal to 2. So now also there is one condition, that means the assumption of L is equal to 0 stage which we made in calculating the depth of potential well is thus pretty good. That means almost most of the time, 96% of the time it is L is equal to 0. But not quite exact. This meaning of this is that 4% time it is L is equal to 2. And now electric quadrupole moment. The bare neutron and proton, that means single proton and a single neutron. That is the bare meaning. The bare neutron and proton have no electric quadrupole moment. That means they have some charge symmetry. And so any measured non-zero value of the quadrupole moment must be due to the orbital motion. Thus, the pure L is equal to 0 wave function have no quadrupole moment. That is known to us. L is equal to 0 means S state. S state you are considering the shape as somewhat spherically symmetric. And only for PD etc. you have some dumbbell shape. This is actually, these terms are known to you from your electronic orbits and not here. But I am just using the same terms here. So the observed quadrupole moment you are getting as 0.00288 plus 0, this is the correction factor, and this B stands for barn, BARN. Actually, you know that barn is the unit for area that we are using in nuclear reactions, and 1 barn is equal to 10 raised to minus 28 square meter, 10 to the power of minus 28 meter square. And you are normally representing the quadrupole moment in terms of area, that is barn. So this is very small in comparison with any other nuclei, but certainly not C. So the mixed wave function psi is equal to AS psi of L is equal to 0 plus AD psi of AC L is equal to 2 is used to evaluate P. So it gives two contributions, one proportional to AD square and another proportional to the cross term AS and AD, or AS into D, AD. And this is you are normally getting from some tensor type calculations. So performing the calculation, we get Q as root of 2 by 10 ASAD R square SD plus 1 by 20 AD square R square DD. And this R square SD and R square DD can be calculated using some techniques. And you can substitute this AS and AD, or AS square and AD square. Sorry, here AS into AD and here AD square. You know these values AS and AD. So you can get that value. To calculate Q, we must know the Deuteron D wave function, D state wave function, which is not directly measurable. Using the realistic phenomenological potentials gives reasonable values of Q with the D state admixtures of several percent. Admixture means it is a mixture of D state and S state. And it is consistent with the value of 4% deduced from magnetic moment. So here also you can see that the value of D state is nearly 4%. And scattering experiments using deuterons as targets also give D state admixtures in the range of 4%. Thus, our conclusions from the magnetic dipole and electric quadrupole moments may be valid at all. So that condition, 96% time it is S state, 4% time it is D state, is correct. Based on these conditions, you can say that. And that's all in this class. So, in next unit, we will start with the nucleon scattering. And that's all. Thank you.